Alright guys, so I know some of you wanted some help with the atomic radii, the ionization energy, and the electronegativity trends and how to put them in order from largest to smallest or vice versa from smallest to largest. So real quick video, I'm going to try to go as fast as I possibly can without going too fast. So let's start off with our atomic radii. Okay. So first I'm going to work within the groups, so going down, so I'll just work with group 2A there to start off. And to do that I'm going to switch over from my periodic table just to a regular piece of paper here. So as I go down on my group, we're going to start off on top with beryllium. So just a real quick model here. We have beryllium and it's in our second period, so we're going to have 2 energy shells for beryllium. All right, now if we're going straight down group 2A, our next element is magnesium, so that's Mg, and it is in our third period going across. So since it's in our third period, we're going to have 1, 2, 3 shells. Okay. So if we look at these two pictures here, we have beryllium with 2 energy shells, magnesium with 1, 2, 3 energy shells. So what this tells us is, obviously, since magnesium has more energy shells than beryllium, it's going to be the bigger atom. So if I go back to our periodic table here, as I go down, I'm just going to abbreviate it AR, atomic radius, is going to increase due to more energy shells. Okay, that one's pretty simple. So let me just get a new periodic table here just so we can see the periods a little bit better, so I don't keep everything real squished up together. So as we go across a period, let me use, I don't know, period 4, and I will use our D block. I think it'll be pretty easy. We'll go in from the S to the D, and everything, even though this is 3D, everything in this period is going to have 4 shells, 4 energy shells. So I'm going to start off with our potassium, and I'm going to draw potassium, and then I'm going to move over to 3D10, which is zinc, and I'm going to draw 2 real quick representations of them. So I have potassium, which is K, and it's in our 4th period, so we're going to have 1, 2, 3, 4 shells. And I also am going to have zinc. Again, we said that's 3D10. And it's also going to have 1, 2, 3, 4. Now, they're both going to have 1, 2, 3, 4 shells. And same thing with potassium. 1, 2, 3, 4 shells. So they're going to be fairly even in their size, but there's going to be slight variations. Now, with zinc, if we look at our atomic number for zinc, it's going to have 30 protons, and potassium is going to have 19 protons. So just like in cell biology, where we have our nucleus, which is the control center of the cell, same thing goes with in chemistry with our atoms. You know how I hate the English language so much, how we have nuclei that are both in cells and atoms, and they're the same word but they mean slightly different things. So anyway, but just like in biology, it's the control center of the cell. As we have more protons in there, it's like a bigger control center. It can do other things. It's a stronger atom. So it's almost like zinc is the guy with the big muscles, and potassium, alright, not so big. So what zinc is able to do is it's able to use these strong muscles, these large number of protons, and it's able to reach out to that valence shell 30 times to be exact with all those protons. So it's able to reach out to all of them. And what it's able to do, I'm not going to draw this 30 times, is it's able to bring it in, that valence shell, slightly closer by the attraction of the positive protons to the negative electrons. So because it has more protons and we have the same number of shells, it's able to just bring those valence electrons in a little bit closer. Overall, it's just a stronger element, and you could think of it that way. Alright, so as we go across this way, our atomic radius decreases, and this is due to the increased number of protons. Okay, so let me do a quick example with atomic radius. Let's use, I don't know, vanadium, sulfur, mercury, iron, selenium, and some tungsten. First thing I like to do is go to my periodic table, find them all. We got sulfur, we got selenium. Here's a little bit of iron, there's some mercury, tungsten's there. Lastly, we have vanadium. Now, if you recall from class, our largest element on the periodic table was francium, bottom left, and our smallest element is going to be helium, top right. So, given that, what we're going to do is we're going to start at the bottom left of period 7, and we're just going to go across the periods, and this is going to be our biggest, and we're going to go across, and as we go across, we're going to get smaller and smaller and smaller and smaller until we reach the end, and then we're going to go to the next period. We're starting with the biggest element in that period, which is period 6, cesium, and then we're going to go across and get smaller and smaller and smaller and smaller up to period 5, and so on and so forth. So, if we start here, going across, there's nothing in period 7, so let's move up to period 6. Oh, there's my W, there's my tungsten. So that's going to be our biggest element. And we're just going to continue across there. We're not going to worry about any other periods right now, and we get to mercury, which is Hg. So that's our second one. Third one, all right, I'm done with period 6. Let's go to period 5. Let's go across there, nothing there. So now we're in period 4, and I have 3 elements in there. So again, as I go across, it's going to decrease. So I want to start with our biggest ones, which would be vanadium. And then we have iron, and then selenium. And we're done with that period. And our last one, go to period 3, we go over, it is sulfur. So this is our atomic radii listed from largest to smallest. All right, so there's a nice example for you guys. Hopefully that helped out. Next things we got to go over are our ionization energy and our electronegativity. Richie's done nice for you guys. Just to review, so ionization energy, I abbreviated it I.E, is our energy needed to remove an electron. If we're talking about the first ionization energy, that is our energy needed to remove one or the first electron. And it's always going to be from that valence shell. We're not going to touch any of the electrons from any of the inner shells. Electronegativity is the ability of an atom to attract electrons. So let's start off with ionization energy. Now let's recall that our groups are alkali metals, 1A, alkali earth metals, 2A. Come over to our boron group, 3A, carbon, 4A, nitrogen, 5A, oxygen, 6A, fluorine group, which is our halogens, is 7A, and lastly our noble gases is 8A. Those numbers in front of the A correspond to how many valence electrons there are in that atom. So it would go 1, 2, 3, 4, 5, 6, 7, and lastly 8. Now let's work with those ionization energies, and let's work across a period first. We'll start that way. So if I'm going across a period, I'm going to start over here just with the alkali metals, and I'm going to draw really any one, and I'm not going to worry about that valence shell. So I'll just write 1A, so you guys know that we're working with 1A. Now that 1 means we have one valence electron. So if I put that valence electron in there, There it is. Okay, nice one valence electron. Now, it wants to be noble-like. It wants to become like our celebrities of the noble gases over here. But it only has one valence electron. Now, in order to get to 8, it would have to do one of two things. It can either gain 7, or it could lose 1. It's always going to pick that lower number, so it's going to lose that electron. Let me come over to the other side. Say I'm in 7A now. And I will draw any of them, I guess. 1, 2, 3, 4, 5, 6, and lastly 7 valence electrons. So what we're going to do here is we have 7, we have to get to 8, so we're actually just going to bring another electron in, so this one is going to gain electrons. All right, now let's recall, ionization energy is the energy needed to remove an electron. Remove. It is a synonym for lose. So over here, these ones naturally want to lose an electron, is what they want to do. So they are going to lose them very easily, and it's not going to require a whole lot of energy. However, these ones over here with 7A, they want absolutely nothing to do with losing electrons. In fact, they want to do the opposite in gaining electrons. So as we go across a period, our ionization energy is going to increase, because it's going to take more energy to remove those electrons, since the ones over here want to naturally gain those electrons to have that full shell, instead of losing them to have the full shell like the metals on the left side are in groups 1A, 2A, and 3A. All right. Now, let's talk about our periods. These are where it gets a little bit more... Okay, sorry, my last video, it just decided it wanted to take an easy day and not film the rest. But anyway, I'll splice the two together hopefully and it'll be okay. But anyway, we ended up finishing the periods on ionization energy, so let's get to the groups next. Best way I can do this is I'm going to work over here on the 7A group, and we'll go down that group. If I go up here to fluorine, we're working in the second period, so let me draw a very brief model of fluorine here. Since it's in our second period, we're going to have 2 shells. And I have chlorine, which is right underneath of it in the group, and we're going to have 1, 2, 3 shells. Alright? Now, if we look, we have 1, 2 for fluorine, 1, 2, 3 for chlorine. Big thing to do with this is think about it as we have our nucleus and it's trying to pull that valence shell in. Now, the closer that valence shell is to the nucleus, the easier it is going to be for the nucleus to protect those electrons in the outside shell. If they're further away, it's going to be harder for them to protect it. So for chlorine, we are going to have our valence shell that's 3 away. For fluorine, it's going to be 2 away. So it's almost like an unruly kid. They're further away from the nucleus, so they can kind of run amok and do things like that. But if they're real close, the nucleus can watch those electrons and make sure they stay there. So recall that ionization energy is the energy needed to remove an electron. So if the electrons are closer to the nucleus, like in fluorine, it's going to take a lot more energy to remove them because the nucleus is right there guarding it. Whereas for chlorine, it's a little bit further away. So overall, as we go down a group, our ionization energy is going to decrease. Okay? Alright, so let's do a real quick example with this. Let's say I have TC, TE, PD, PO, BA, and lastly SR. So first thing to do, let's find them all. TE, there's PO, there's PD, there's TC, SR, and BA. Okay. What you want to do is you want to start up here on the top right, and we're going to work our way down through the groups. Okay, so and we're just going to see which ones we run into first. So we go down the first group, down the second group, and we run into T, E, and then PO. And we just keep working our way over, nothing, 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 until we hit PD, which will be next. Work your way down, back up to the next, work your way down, back up to the next, work your way down. You get what I'm saying. Keep working your way over, and we run into group 2A. It's going to be strontium, which is first towards the top of the group, and then barium right underneath of it. So there is your correct answer. Okay? So TE, PO, PD, TC, SR, and lastly BA. Okay? Lastly, for electronegativity, it's actually going to be the same exact trend for ionization energy, where we are going to increase as we go across and decrease as we go down. Now, recall that electronegativity is the ability of an atom to attract electrons. They work hand in hand, because ionization energy is the energy needed to remove an electron, and if an electron is being removed, it's not going to want to attract electrons because it's actually trying to get rid of them. Same thing if the other way, if we're trying to gain electrons, it's obviously going to want to attract the electrons. So if we have this, we're increasing going across a period, decreasing going down. Quick example I just made up real quick, and this is going to be the same exact thing as ionization energy. We're just going to go up, down, start at the top, go down. Tin, hafnium, potassium, calcium, lithium, and titanium. I circled them all for us there. So we're going to come here, go down, nothing. Come here, down, nothing, until we reach carbon. That's going to be our first one, followed by tin, which is going to be our second. Keep going over. I don't see anything here until we hit titanium. That's our next one over. So that's going to go first, go down our titanium group. We run into hafnium. And then we go up, nothing in that group, go up, nothing in that group, go up one more time. And we have lithium. And underneath lithium we have potassium. Alright. So hopefully this helped you guys out. Have a good rest of your weekend. Make sure you study. And I'll see you guys on Monday.